This is outlining the size that the crack grew to before the material broke. So it reached the critical stress intensity factor when the crack grew from this size finally to this size. And what we have, how that works is this is a graph of the velocity of the crack growth as the stress intensity factor increases. So on y-axis, this natural log of v is the logarithm of the crack growth velocity. And so that initial pour generates a crack which begins to slowly grow. In the patient, maybe it's growing at the rate of micrometers per week, micrometers per month. And then as it begins to grow, we see that that increases the stress intensity factor, even at constant stress, and that results in a faster rate of crack growth. And so the crack accelerates. It's a vicious cycle. And then it will grow a little bit larger. And eventually, when it reaches the size of the critical flaw, we will be at this critical stress intensity factor, K1C. And then all of a sudden, the crack goes from growing at the rate of micrometers per month to meters per second, and you see failure of the restoration. Okay, I said that we had two mechanisms for fatigue crack growth, and the second one is called cyclic fatigue. And in cyclic fatigue is very similar to stress corrosion, except it requires a chewing motion. It requires a loading and unloading, or in the case, well, you mentioned hydraulic pumping, perhaps too. And so in cyclic fatigue, you see a graph of the velocity of the crack growth versus the stress intensity factor. However, it's a little bit different, because instead of the stress intensity factor, we have delta K, which is the amplitude or the fluctuation in stress intensity factor. And instead of just K on the x-axis down here, we have a logarithmic x-axis in the case of cyclic fatigue. It's linear for stress corrosion. And you see here that instead of the crack size changing over time, the crack size is changing with respect to capital N, which is the number of cycles until failure. And we can see that on the surface of some implants that have fractured in our lab recently. You can look near the origin of failure on the implant body at the root of a screw thread, and you can see these fatigue striations. And it creates one of these striations every time the crack advances a little bit further. It grows little by little, and those make a mark on the fracture surface. You can look in the microscope later and see how fast the crack was going. And then if we look farther away from the failure origin, where the stress intensity factor has become higher, by the time the crack is reached there, you see the fatigue striations are larger in size. Okay, so this magnification is 4,000 times, and this is 7,000 times. So these fatigue striations are much, much larger than these fatigue striations. So the crack is gaining in velocity as it gains in size. And then zooming out to look at the entire specimen, we can see that at the origin here, we are producing fatigue striations on the fracture surface, and eventually the crack reaches a critical size, critical stress intensity factor, and then fast fracture happens. And we get a different look to the fracture surface. We see the ductile dimples from tearing of the metal all in one event instead of fatigue over time on the rest of the fracture surface. So just to summarize that, we have two mechanisms for subcritical crack growth. One is stress corrosion, the other is cyclic fatigue. And the main differences are that stress corrosion does not depend on the frequency of cycling. And we're going to talk in a minute about designing fatigue tests. So it's important to remember that if you're testing a material that does not have cyclic fatigue, if it only has stress corrosion active in that material, then it doesn't matter if you test the material at a faster rate of cycling. You will not drive the cracks to go any faster. However, the cyclic fatigue does have a frequency effect. The crack growth is is measured in terms of micrometers per cycle. So the cycling is necessary, and the frequency of testing has a strong effect. Stress corrosion is dependent on the stress level, could be a constant stress level driving the crack. However, the cyclic fatigue is dependent on the stress range, or the amount of fluctuation in stress level, and the ratio of the minimum to maximum stress during the fluctuation. And so why is it important to differentiate between these two mechanisms? Because some materials show one mechanism and other materials show the other one. So in stress corrosion, we typically see that in ceramic materials, porcelains, glass ceramics, polycrystalline ceramics, and in the case of some metals, limited amount of stress corrosion. But cyclic fatigue, we usually think about occurring in metals, not ceramics. However, that has been observed in some polycrystalline ceramics, some of our stronger materials like zirconia. So you may be testing the material that has both of those mechanisms active at the same time. So I mentioned in Mississippi we have a lot of nature, and if you mention to somebody from the United States, Brazil, the first thing that they will probably think about is dangerous animals from the Amazon, right? Giant snakes or alligators. So we have that. We have the alligators in Mississippi also. It's a very natural place. But you have to be careful about keeping them in the background because they like to be the center of attention in the photograph. Okay, so these cracks are going to go through the materials and weaken the restoration over time. And we would like to be able to predict how long it's going to take for that to happen. And we can do that with clinical studies. If you follow a bunch of clinical studies in the literature and combine the data together into a Kaplan-Meier survival analysis, this is the type of graph where the y-axis tells the percentage of restorations that are still surviving at each point in time, and the x-axis is the length of time you have been following the restorations. And we can even begin to note some patterns, like the processing method used to form the material into the shape of the restoration. Inlays and onlays, you can look at pressable materials lasting longer over time than, say, CAD-CAM products, which last longer than a powder porcelain, which is condensed. And we can also notice some patterns like for the all-ceramic fixed partial dentures that there is a higher survival rate in the anterior than there is in the posterior for a given material because the lighter biting forces in the anterior. And that if we make, not according to manufacturer's recommendations, but use smaller connector area for better aesthetics, that we can run into trouble and have a much lower survival rate. Okay, so we can get a lot of good information from the clinical studies, but once the material is out in the clinic, it takes a long time to follow it, and then it's too late to do something with our information to make sure that it has the proper indications. So what we would like is an in vitro test, a rapid in vitro test, where we can test new materials that we are producing and make sure that they are applied properly in dentistry. And that's the main point I want to talk about today, is lifetime prediction. And I'll tell you a little bit about there are two approaches. There's a virtual approach to lifetime prediction and a physical approach, and we will concentrate on the physical approach today. So just briefly, in the virtual approach, in that method, we don't actually test a restoration in the laboratory. Instead, we shape the material into the shape of standardized specimens with an ideal geometry. For example, some of these 3-point, or in this case 4-point flexure bars that you have seen from the other presenters this morning. And then we subject that to a bending force, and it causes the stress to develop on the bottom and the material to crack. And if we test a lot of those, then we can get information about how fast cracks grow through that material and what size the cracks start in the material. So if we analyze all of the data from testing the specimens together, this type of experiment, we can get the crack growth coefficient and exponent, which tell us at each stress level how fast the cracks are growing. And we can get the Weibull modulus and characteristic lifetime, which tell us the difference in crack size between the initial crack and the critical flaw size. And then we can use finite element modeling. This is where the virtual part comes in. Finite element modeling to calculate a stress distribution in the restoration and put all that information together. Now we have the initial flaw size, the critical flaw size, and the rate that it's going to grow from one to the other. And we can calculate how long it will take to get there. Just like if you're planning to go later this week to Sauipe, then you have to know the difference in distance between where we are now and where we are going and the average speed of the airplane, and you can calculate the time it will take to get there, right? So that's what we do in the virtual approach. However, it has some advantages, but also lots of disadvantages. The advantage is that we can often acquire the data without having fatigue-capable load frames. And we saw some of the presenters this morning have very nice fatigue load frames in their laboratories, but those are quite expensive, and not many laboratories have them. And so it's nice to be able to use a method where you can do a monotonic or a constant stress test to get your data. The big advantage of the virtual method is you can alter your test conditions in just hours. Once you gather all the material data, you can change the angle of force application, change the amount of force biting down on the restoration. You can change the geometry of the restoration and rerun the analysis and get new predictions for lifetimes very rapidly, changing conditions. However, it has many disadvantages. One thing is that if you have a system which is being processed in a furnace, like a veneer ceramic on top of a coarse ceramic material, then it's difficult to model the thermally induced stress using a computer. That can be very challenging to model if there's some viscoelastic relaxation during cooling. Another problem is that with the finite element modeling, usually it's the sharp edges and the interfaces between materials where we're most interested in knowing the stress. And finite element modeling has a bad habit of not converging in these areas, so you don't know if your stress is going to be very accurate in the areas you are most interested in, the likely failure areas of the restoration. And then the computer model involves many assumptions, such as if you use standard geometry specimens, then are those going to have the same initial flaw population as a clinical restoration? Are you going to process them in the same way? In polishing them to make them a standard geometry, maybe you will alter the initial flaw population. And then also similarly, are you going to process them in a way that gives a similar thermal history and results in the same microstructure as you will have in the clinical case? Or will your standard geometry specimen be thicker, be larger than a dental crown material, and therefore have a slower heating and cooling rate and develop a different microstructure and different properties? And however, our laboratory has done some of this virtual approach, and I would like to congratulate my postdoc, Yuan Yuan. She's here in the audience today, and she has become a master at taking the CAT scan and translating it into virtual geometry, assigning material properties, and predicting the stress distribution. And she presented that at the Academy meeting last year. And if you have any questions about that, you can meet and talk with us later. But the rest of the time, I want to focus on the physical approach. And I've lost something here.